And you're required to pick file or block or object because you need performance, you need scale, or you need simplicity or shareability. Unfortunately, these AI workloads need all three, and they need all of them at the same time. They need speed because you're able to process data 10, 100, 1,000 times faster with these GPUs. If you're bolting on, grandfather's storage from 1996 to the back end of it, those GPUs are just going to idle. Those GPUs are costing, $35,000 to $55,000 each. People are buying them in tens, hundreds, thousands, tens of thousands at a time. That is a lot of infrastructure that sits there. We describe these GPU farms. They're like sloths. They're asleep about 70% of the time because the data infrastructure simply cannot serve enough data to them. So it needs to be fast. It needs to be simple and shareable because, particularly in certain types of AI, things like natural language processing, things like sequencing, you were talking about billions of files or billions of objects that are being managed. So you need a very simple way to name and identify those things. And then people are looking at scale. And some of these environments already are getting very, very, very large. We'll talk about some of them in a moment, but many of them are measuring themselves in hundreds of petabytes, kind of into the exabyte size range. So very, very large environments. So they need all the best of all types of storage infrastructure. The second thing is that we talked about many of these workloads going into the cloud, and they need the same performance that they would expect on premises to be able to happening in the cloud. I met the CTO for a large online furniture reseller or retailer probably 6-ish, 8-ish weeks ago now, and he described this perfectly. He said, to the external world, we tell everyone we're a Google Cloud. Internally, we tell everyone we are a Google Cloud customer. And they're like, we are a Google Cloud customer with one exception, which is the 3 workloads that we actually run the business on, and they sit in a data center running on a Ferrari that we built for the last 10 years. And they're like, I know that if I try and move those workloads into the cloud, I'm going to get, at best, 10% of the performance and the throughput that I get today. And I simply cannot run my business in an environment like that. So people are expecting these AI machine learning workloads are very performance intensive workloads. They're very high throughput workloads. They require on-prem like performance that you measure in gigabytes, not gigabits, gigabytes, tens of gigabytes, hundreds of gigabytes, terabytes a second, running inside the cloud. Thirdly, they need to be able to virtualize the data. So VMware 20 years ago did a great job with VMware of taking a physical server, creating a virtual representation of it and running these virtual servers. And by moving away from a physical server model to a virtual server model, you gave those servers mobility. So all of a sudden things like failover between servers became possible, clustering between servers became possible, moving those virtual machines, or more recently those containers. So the virtualized or containerization of compute allowed a whole new slew of capabilities to occur. A lot of these AI workloads require you to do the same thing for data. As we said, many organizations start on the cloud and then repatriate into a data center somewhere. Equally, the fourth point there, many of them are trying to build pipelines for data. They're building a pipeline through which they can flow data, and on top of that pipeline, they're adding lots and lots and lots of different processes, all having access to that data all at the same time. The final thing is that people are using a new stack for AI and machine learning. So if you're involved in this space, we've already talked about data, we've already talked about accelerated compute. There's a slew of other new software layers that sit on top. Containers, TensorFlow, PyTorch, Kubeflow, foundation models, application pipelines. The thing to realize, again, is that many times when people start on this journey, they will use all of the native services that are available. And then when they begin to scale, they want to be able to find, how do I move those native services across different core cloud and edge environments? Because if they start on one cloud and decide for economic security, whatever it may be, reasons they want to move to a second cloud, it makes it very, very easy. If they want to move between on-prem and into the cloud and vice versa, it's very easy. If they want to build pipelines that are abstract from the infrastructure of the cloud underneath, it makes it easy. So that, again, for a lot of these large organizations, is the architecture they're building. Common data platform that spans core edge and cloud environments, common application data pipelines that span core edge and cloud environments, and then these ubiquitous stacks that sit in between them. Data sets, well, we already talked that kind of data sets are large. So a lot of people start very, very small. A lot of people start in the tens and hundreds of terabytes, very, very small, but scale pretty exponentially. We have some projects that are less than a year old that are knocking on the door of an exabyte in size. So we work with the DOE on something called the Vera Rubin's telescope in Chile, where they take a snapshot of the known universe every 3 seconds. Each of those snapshots is about 30 terabytes in size. It's a 17 gigapixel camera strapped on the back of the telescope. They dump that into a Weka, and then they run computer vision AI on the frame, and they create a digital twin of the universe. And then on the digital twin, they run a second set of algorithms that determine, are any of these objects going to, and they're looking at every asteroid, meteorite, piece of space junk, satellite, to determine, are any of these objects going to hit each other, and more importantly, is the result of that object going to hit Earth? There's something called the planetary protection system. They, by the end of this year, will be having over an exabyte of data in that system. So we're starting to see that these environments become very large. I don't know whether anyone read the Economist article from 2 or 3 weeks ago, which talked about this issue. A lot of, obviously, things like ChatGPT and things were trained on 100 million YouTube videos. That's the kind of the call for ChatGPT 4. A lot of people saying that that by the end of next year, the internet is going to run out of data to be able to train these models. So now people spending a lot of time building synthetic data, larger and larger and larger synthetic data sets to continue to train these models at scale. So the data sets become enormous very, very, very quickly. So when we turn up an environment, this is what we tend to find, is people have got religion about GPUs, got religion about accelerated compute, they've got religion about fast networking, and they're trying to build a data pipeline. So they're trying to ingest data on the left-hand side, and then once they've ingested the data, they're going to do some kind of pre-processing. They might be ingesting data from lots and lots of different sources. They're pulling in like bananas, oranges, and apples, and they just want to all homogenize it into fruit, so they'll do some processing to do that. Or they want to start tagging and labeling and those sort of things of the data they're ingesting. Then you get into the exciting stuff. You want to begin to train your model. Once you train the model, then you want to be able to spin that model up 10, 100, 1,000, 1,000,000 times and stream the same data to it to validate that it does what it says it's going to do. Then you want to move it into inference, you want to move it into production, and then you'll do some archiving. And what they're doing is they're building different data stacks underneath each of those, because in the world of ERP and CRM, that's what you did. You racked and stacked a bunch of gear, you tuned the heck out of it for 6 months, and then you just let it run. That's exactly what they're doing here. They'll build an ingestion stack, and they will tune that ingestion stack for 100% write performance. If you could deliver, as close to 100% write performance as you can, that's what you would do. The fastest write performance you could do, the faster you can write information, the faster you can ingest data. Then they'll do some kind of pre-processing, and then they get into training the model. Training is the opposite of ingestion. When you're training the model, the only thing you care about is how fast you can read data. The faster you can read data into these GPUs, the faster you can train the model. The faster you can train the model, the more you can shrink the epoch time. The more you can shrink the epoch time, the more times you can do the epoch in a 24-hour day. So you go from only caring about 100% write performance to only caring about 100% read performance. Then when you get to validation, it's a different stack again, different I/O profile. When you're validating a model, all you care about is not read performance, not write performance, you just care about streams performance. Can I get the same data set and stream it 10, 100, 1,000, 1,000,000 times to the same model to make sure that the model you trained does exactly what you think it is going to do. Then you move into inference, you go into production, and in production you don't care about read performance, you don't care about write performance, you don't care about streaming, all you care about is the lowest latency possible. If you're in your autonomous driving car and you get to the intersection, you don't want it to wait for 5 seconds when it figures out whether it's going to go left or right. You want the lowest latency possible, you just want it to make the decision and go. And then finally, if you're in any regulated or semi-regulated industry, you need to archive that data, typically for the lifetime of the product, because if the car does turn left and hit a pedestrian, in all likelihood you're going to be subpoenaed for the algorithm and the data set that was used against that algorithm back in 2018 that determined that the car should turn left. So people are building lots and lots and lots of stacks. They're tuning each of these stacks for I/O, or particular types of I/O, and then they're employing an army of people. It's a cool new job title called a data engineer. Sounds very exciting. Most of the time, data engineers are glorified copy monkeys. They're just copying huge amounts of data from one stack to the next stack to the next stack to the next stack. It's very slow, it's very labor intensive, it's very prone to failure. Doesn't really work at scale. Doing it in the kitchen sink with a gigabyte of data, no problem. Trying to do it with half an exabyte, completely different issue. So when we turn up, this is what we do. Instead of building all these stacks, we get the infrastructure and we build a software layer that goes across the infrastructure. It's a parallel data platform. It allows you to ingest data through traditional protocols like POSIX or SMB or NFS, or some more exotic ones like HDFS or GPU direct storage, and you can ingest data. As soon as data is ingested into the platform, then you can have 1, 2, 10, 50, 100, 1,000 other processes begin to access that data. By doing that, you're beginning to create a processing pipeline, where you're beginning to move data through that pipeline. So to the same data that you just ingested, and you're maximizing write performance here, you can read the data, you can stream the data, you can provide the lowest latency or archive for the data. Effectively, what the Weka data platform allows you to do is separate the data itself from the way that the data is accessed. And we can deliver you incredibly fast access to the data through the protocol of choice that you want, and we will deliver I/O perfectly to every single workload. On average, this will perform somewhere between 10 and 100 times faster than anything else that you're using. So it is incredibly, incredibly fast. We post numbers of 2, 3, 4 terabytes a second in the cloud. Most tuned data centers for the last 10, 20 years don't deliver a terabyte a second in the cloud of throughput. So we provide incredibly fast throughput on-prem, in the cloud, or out at the edge. We scale effectively infinitely. We start at a single terabyte, we go up to 14 exabytes. That is obviously a limit. We haven't met anybody that's hit anywhere close to that limit yet, but I would say probably within the next 5 years we will. And typically, the cost of this environment is about a quarter of the cost of anything comparable. The reason is because we have what we call incredible performance density. For the same number of cores, the same amount of network, the same amount of RAM, because of the parallel nature of the platform, we're able to drive much greater performance density. For the same set of hardware, we'll drive 10 to 100 times better performance. Not only can we run different steps in the pipeline on top of the platform, we can actually also run different types of of AI on top of the platform as well. So we met a customer, they shared a perfect example a few weeks ago in Seattle, and they were a pathology lab, and they were taking slices of mouse brains, and it's a 2 to 3 nanometer slice. They put it on a slide and they take a picture of it. And they said, what they're doing today is they're taking those pictures and they're stacking all the pictures up and stacking them up, and they'll put hundreds or thousands of pictures stacked on top of each other, and they would be able to build a 3D representation of a tumour. From their point of view, if you've got to wait to be able to find the tumour, that's kind of already too late. So what they're trying to do is they're taking this slice and they're zooming into the slice, and it's like an aerial photograph. You zoom in 10 times, it gets a bit scratchy. You zoom in 100 times, and it becomes somewhat unintelligible. So they're zooming in 2 or 3 times, and then they have a set of generative algorithms that will redraw the frame. It takes all of the blockiness, all of the squareness out of the frame, and it redraws the frame. And then it zooms in 3 more times, and it redraws the frame. And it zooms in 3 more times, and and it will do that process somewhere between 100 and 1,000 times. By doing that, the frame is still perfect, but you're now down to being able to see individual cells in the frame. And then they run a second type of AI, which is a computer vision AI pipeline, which looks at those pictures and is able to determine which cells have a higher propensity to go cancerous over a period of time. And he stated that by doing that, they'll be able to do discovery of cancers, certain types of cancers, somewhere between 10 and 15 years earlier than waiting to find a tumour. So 2 very, very different types of AI, all utilising the same data in that pipeline. So as I said, each type of AI, and there's lots of different definitions. We use these standard 5. If you're doing natural language processing, so if you're trying to take symbols, tokens, words, and take words and figure out how words turn letters turn into words, and words turn into sentences, and sentences turn into paragraphs, and paragraphs turn into meaning, then it's not a particularly high I/O or throughput environment, but you do have lots and lots of files. Hundreds of millions of files, billions of files if you're doing natural language processing. If you're doing sequencing, so taking similar concepts to that, but using those ideas of finding meaning in tokens or objects, then so things like DNA sequencing uses the same concepts as trying to find meaning in letters and words. It's a different use case. So if you're doing sequencing, again, more reading and writing, but because of there's lots of reasons, but slightly different. If you're doing computer vision AI, so if you're doing AI on pictures or you're doing AI on video, obviously lot higher bandwidth requirements relative to NLP, smaller numbers of files. High performance data analytics, different again. Generative kind of needs the best of all worlds, primarily because generative is very, very broad and wide in its definition today. When we say we're fast, this is just a graphical representation of using kind of cloud native services or even exotic parallel file system type